So in today's presentation, I'm going to go over neural image caption generation with visual attention. This is the article that our group is working on. So in our first lecture, we went over a general overview of this article and how we could generate image captions. In today's lecture, we're going to go over a few selected topics. We're going to go over the LSTM, and we're going to go over the attention mechanism. This video is going to go over the attention mechanism, and I will be presenting that part. So this picture that you see on the right, this is a part of a real data set. I believe it was the Flickr 8K. This picture is from that data set. And previously we've seen images with only one kind of option, a dog or cat or a cub, and then a CNN was able to classify that one image as either a dog or a cat or as a cub based on the features and the feature maps that are extracted from the image. What this article is trying to do is kind of a generalization of that kind of one object classification task. Instead of one object, we have multiple different objects. And not only do we have multiple different objects, we have to understand the relationships between those objects. And in doing so, we'll be able to have a scene and then classify a descriptive sentence about it. In this case, these are called captions. So that is the goal of what this article is trying to do. We're trying to get a very complicated scene. And here we can see two individuals talking to each other next to two bikes, next to a swamp. So not only does the model need to understand the different objects that are there, the people, the bikes, and the swamp, but also their relationships between one another. That there are two people next to a swamp with their bikes talking to each other. This is the goal. Previous research, they tried to take an image like this and at every time step to render the entire whole image into a decoder system and then decode a word at every time step. But in this research, we're trying to suppress the amount of information going into a decoder. We're trying to limit that amount, and in doing so, we will get a much more efficient model. And as we saw in the previous presentation, a model that has state-of-the-art accuracy as well. So the kind of metaphor between human intelligence and artificial intelligence is when we look at an image like this, we are not looking at it holistically in one viewpoint and then understanding exactly what is going on in the scene. Instead, when we get an image like this, we take a look at it, we take a few glimpses, or the physiological term is the saccades. We take a few glimpses, and then we see there's two people and there's two bikes, and then maybe we take a look at the swamp behind them and see it's a park. And then we are able to see there's two people with their bikes next to a swamp. And here, this is exactly what we're trying to model. We're trying to take these glimpses at every time step and then come to a general idea about what's going on. So this is taken atomistically. This is how we're trying to model something that is related to how people actually do their perception. So if we wanted to sample different locations, and this is what we're trying to do, we're trying to go over and sample different locations. If you wanted to mathematically do any kind of sampling, we need a distribution to sample from. And in the case of this article, we're going to use the multi-Newly distribution. So previously in our class we had a problem where we dealt with the binomial distribution. When we dealt with the binomial distribution, we had a probability event where we rolled, where we flipped a coin, and there was only two discrete outcomes. It was either heads or it was either tails. And we flipped this coin multiple times, more than once. When we have data in this kind of form, where we have two different discrete outcomes, we could model this data into a binomial distribution, and then we could get summary statistics about our data within this distribution, such as the mean, the variance, and so on. Or we could do probability statements and say, well, given our data, what is the probability that out of 5 flips of the coin, I'll get 2 heads? Now in a Bernoulli, we only have n is equal to 1, so the difference between the binomial and the Bernoulli is that we only have one trial of this probability event. So we only have one flip of the coin. And this is parameterized by p, the probability at each outcome, each of the two distinct outcomes. So if I flip a coin once, if I have this data about flipping a coin and I wanted to model in one flip of a coin how much, what's the probability that I'll get a heads, I could use the Bernoulli to find that kind of probability statement, and also I could do summary statistics like the mean and the variance as well. We're going to generalize these two into the multinull and the multinomial. So here we had two discrete events, either a heads or a tails. But then when we have, in the case of the multinulli, when we have a discrete an outcome that has more than two different categories, it has more than just heads and tails, we could model this data and fit it into a multinulli distribution. So instead of having a coin, we'll have a dice where we could roll a 1, a 2, a 3, a 4, or a 5, or a 6. So we have 6 different outcomes, and then we have a probability at each one of those different outcomes. This is parameterized by P of I. And so again, if we have this kind of data, a die roll, then we could fit it in this kind of form into a multinulli distribution, do summary statistics again, or we could do probability statements, like if I roll the die one time, what is the probability, given my data, that it will be a 4 that I roll? The multinomial further generalizes this and has, again, a trial greater than just 1. So if we take this die roll and we flip the die multiple times, and then we want to ask, what is the probability that out of 3 die rolls, I will get 2 2s. I would use a multinomial distribution to find my answer to that probability statement. Again, I could do summary statistics, find mean, variance, and all sorts of things with just fitting data into a distribution. In our case, in the case of this model, we're going to use the multinulli. And this is how the multinulli in an abstract general way will help us sample different locations of an image. If you have an image like divided into, say, these 4 parts, just for understanding, and say, here's image location 1, here's 2, here's 3, and here's 4. Now we have an outcome here, we have an outcome here, we have an outcome here, and another one here. So multiple different outcomes. This is how it fits the multi-nully. And then we want to find a probability here, here, and here, and here. And this probability statement that we are going to use is right above here. Probability of S of t of I equal to 1 given Sj less than t, and our annotation vectors is equal to alpha t of I. This is the probability statement that we're going to use to find the weights at each image location. And here we have alpha, which in our case is going to be same as p, the probability. So we have, what is the probability that given our attention locations that will be randomly sampled is equal to 1? Meaning this is the place that we want to attend to. So what is the probability that this location is where we want to attend to given previously selected 4 image locations and given all of the feature maps from our CNN that have been extracted at these locations? That is going to be equal to alpha at time t at location I. So each one of these is going to be given an alpha value based on this probability statement. And so with this model, to review, when we had a higher probability, that meant that this area would be more selected to in our decoder, would represent more of the information in the entire image into the decoder. And we would have, like say, if here we had a high probability and here was low, we would attend to here. And each one of these different probabilities, because we're using a multi-nully, would sum into 1. And again, this is going to be discrete, so it's not going to be in a continuous form. There's going to be one area selected for other areas, not so much, or not at all. And we see here our sampled locations at time t iteration I varies as a multi-nully based on our annotation vectors from our CNN, parameterized by the alpha value, these p values, iteration n, location I. So to recap, in our previous presentation, the annotation mechanism needs to compute a context vector z of t, and z of t being the attention, or in the researcher's words, representation of the relevant part of the image input at time t. Here, we treat z of t as a random variable that changes over time t. So we have z of t, an estimate of it, and phi is a function based on this article had two different attention mechanisms. We're going to use stochastic hard attention, so that's going to be what phi is here. And we have two inputs. We have those feature maps taken from our CNN, and then we have the weights at each one of those I locations. Again, restating this is the annotation vectors L at A of I, which are the feature vectors, feature maps, that are created from the encoding CNN, are inputted into the attention mechanism. These are a representation of part of the image at different image locations. The attention mechanism needs to compute the weights alpha at each A of I, and then here we're doing hard stochastic attention, which in the researcher's own words, they compute these weights alpha for each location I as what the probability is that location I is the right place to focus for producing the next word. So here we need to create a new learning rule or objective function that will select for these locations, randomly sample these locations in a way which those locations will give us the highest probability of having the correct caption given all the feature maps given to us by our CNN encoder. So we need to create a new objective function to do this for us in our model. So here's our learning rule. We have the marginal log likelihood. This is the log of the probability of y caption given the annotation vectors, the set in A. And this, we want to optimize this marginal log likelihood to get to our objective function, our learning rule. But this distribution is an intractable posterior distribution, so we're using Bayesian statistics here. And now that it's intractable, we could use variational Bayes, as in the case of what the authors did, to approximate a theoretical distribution to form an empirical distribution that is close in the sense of KL divergence. So we don't have access to this distribution for either one or two reasons, maybe because it's computationally expensive and impractical to do, or maybe because we don't have direct access to this distribution. It's something that is an unknown distribution and we cannot easily work with that. So instead we're going to approximate it and we're going to use variational Bayes. So here's the process in variational Bayes. So instead of maximizing the marginal log likelihood, we're going to maximize a variational lower bound of it. And this lower bound is called the evidence lower bound, mostly because this is the evidence, and then we have the lower bound of that evidence. And we could find an inequality from our marginal log likelihood from Jensen's inequality directly. When we use that, we could form an inequality of this sort. And here we have the lower bound, which is on the left side of the less than, and then we have an upper bound, which is on the right side of the less than. So we can take, so this was the lower bound, this was the upper bound, and this is the elbow now. Again, what we want to do is train the stochastic hard attention mechanism by maximizing an approximate variational lower bound on the marginal log likelihood of observing the sequence of words Y given image features A. So the first thing we're going to do is we're going to take the derivative of the lower bound with respect to our model parameter W, the weights. Remember, that's the alpha here. And we're going to do this using the product rule. So here we have U, and then we have, we're doing the maximization of this. This is the elbow. We have U, and then we have V. So we have U times the derivative of V with respect to W, and then we add that to V times the derivative of U with respect to W. So this is something similar to using stochastic gradient descent, but instead, because we're working with the distribution and we're trying to do Bayesian inference to an approximate distribution, we're going to use the Monte Carlo method to sample these different image locations. We're going to sample from the multi-Nulli distribution, and then we're going to take the derivative with respect to the weights of this distribution to approximate the gradient. So here we have, in summary for the notation, we have set of our sampled attention locations S at iteration n, and then we have SFT when we sample from the multi-newly distribution defined before. So this is our final learning rule, and in this final learning rule we also have two different regularizers included, and we're doing this to reduce the variance of the learning rule, and these are specifically called in the literature control variance. The variance needs to be reduced because when we're doing variational Bayes, usually this method leads to a high variance. So we could add these control variants to reduce the variance, but then keep the expectation the same. So again, in the stochastic gradient estimates of the stochastic hard attention model, there is high variance, and we use these two, moving average baseline technique, and we also add the gradient of the entropy of the multi-newly distribution. This model also has two hyperparameters added to it, lambda r and lambda e. So here's the main idea. We're going to create a maximum likelihood function as the learning rule. We're going to create a learning rule that gives us a function for the maximum likelihood that the attention region is where to focus on, based on optimizing this function with respect to the weights, the parameters of the multi-newly distribution at iterations of different sampled locations. In other words, we are going to find the most probable locations to attend to that lead to the correct caption. We're going to model this into a function, a maximum likelihood function, to maximize this probability. We're going to minimize the variance of this estimator using control variance. And again, we compute these weights based on this learning rule from the sampled multi-newly locations. The weight is the probability that attention location I is the correct place to attend to given any previously selected for attention locations and the annotation vectors, which we said it early on. Another few main ideas is the annotation vectors with the feature maps. These were already pre-trained using transfer learning. These feature maps can already be used to classify common objects by name. When we had one object, we could just classify it with the CNN, but then here we had multiple different objects. So here we're going to train the model using the variational Bayes method with Monte Carlo to find the gradients on the image data set, on an image data set that already has captions. So it's going to be trained based on those labels. And the overall outcome is the attention model with the LSTM is now going to be able to pick the most likely locations on each of the annotation vectors of an image to correctly produce a caption. Lastly, I have my references. This one is the article itself, and then this first reference is another model that is very similar to what we did in this review. And here we have two different references for variational Bayes, which was very instructive and very helpful. And also online, I saw that Professor Tamar Broderick, her lectures on variational Bayes was very helpful as well. So thank you, and that's the end of this presentation.